Hi everyone, this is going to be a lecture about the so-called divergence theorem. Let me first review the surface integral of a vector field. So I wrote it in there. It's denoted like this. S is the surface sitting inside three-dimensional space. We usually have this parameterization with a two variable, and this R here is going to be the flat region in UV plane, not necessarily XY plane, YZ plane, or XZ plane. This is could be some abstract or auxiliary plane that you deal with. And F is the vector field. I wrote it here. It has this component P and Q are as a scalar function. And dA is the flat piece delta U times delta V. And what we are multiplying here is this RU cross RV. Let me write that in. So once you have a parameterization, we have this RU cross RV. So R is the position vector, so if you differentiate with respect to u, and that this is what you get. Alright, so what's written down here is what we actually calculate. This cross product part has this determinant expression. So the first component of this cross product here is going to be multiplied with the first component of f, which is p. First component of this cross product is this determinant of this 2 by 2 matrix there, where y and z is there, so you get that. Q part is the second component. This is this one. So second component is the determinant of this xu xv and zu zv, but there is this negative alternating sign for the cross product formula. So instead of putting the negative in there, I swap the two columns such that x column appeared in the second slot and z appeared in the first slot. So that absorbs the negative into it. R is the z component of the vector field multiplied to the z component of this cross product, which is this determinant of x and y there. So this is actual formula that if you have parameter and parametric equation, and this is missing dA, so if you multiply the dA there, and that's what it is. I assume this wedge product notation, if you don't know what those are, please go to my earlier, probably it's in the pencasted lecture that learned the wedge product notation. This wedge product notation kind of summarizes this determinant part, y in the first column and z in the second column, and they're replaced by just y and z, and introduce so-called parameter-free, parametrization-free notation. So whenever we enter that, we change this R to S, right? So here's notation. So this is the wedge notation I was talking about. So if you replace this y and z with dy wedge dz, z and x dz wedge dx, and x and y dx wedge dy, and pqr is still there. So this does not have a u and v in it, so therefore we just switch to the original object s. And what this means is whenever you have a parameterization, this dy wedge dz is going to be replaced by this determinant in the first column y and second column z with this way of differentiation. So that's the shorthand notation, and again they represent the determinant part. Right, let me show you this much first. What we're about to do is we're about to do the same thing as the Green's theorem, but it's kind of happening in a different dimension. So the first thing we start with here is just looking at the surface S. So in the Green's theorem case, so here's a picture for the Green's theorem case. C is not just an arbitrary curve. C serves as a boundary curve of a simply connected region R. That's how the Green's theorem applies. Something like that. It's the context of the divergence theorem. S is a surface sitting inside three-dimensional space, but it's not like an open surface, such as the following. For example, surface I try to sketch is some like a top of the sphere part, so you can see the bottom part is open end. That's not the S we want to look at here. What we want to look at is the surface S that happens to serve as a boundary of E. This partial symbol here is a standard symbol in differential calculus that is a boundary of solid. So E is actually solid, such as a sphere. So I said a wrong thing. It's supposed to be a solid ball. So if you have a solid ball like this, and E is the whole three-dimensional object. It includes all the inside there, and S serves as a boundary, the surface. So that's the notation here. If that's the situation, so S is not like open end here again, happen to serve as a boundary of a solid like this, and then what we did into the Green's theorem and still works. So what you have to do is that take that P and differentiate, which is represented by this one form dP differential, and introduce another integral. So what really happens in the level of actual iterated integral is exactly the same thing as Green's theorem, but altogether with parameter-free notation, it becomes just a triple integral, and then you have to change that P to dP, which is the differential. Remember that I used the term the chain rule to remind you of what this is. So I wrote it here. That's we have three variables, the main variable for P, so it has to be in this way. So again, this is the shorthand form of what happened as soon as we parameterize it. So the way this one interacts with the other two wedges is two rows, but as soon as we pass from S to E, X and Y and Z are all parameterized with three variables. So like that, passing from here to there, and we go inside the surface S and becoming a solid. So we have to look at all this X, Y, Z as a three variable function. So when you go from and introduce one more integral, we introduce another variable, which is like the scalar factor. That's exactly the correct term to describe how to go inside if we parameterize the boundary with the V and W. Just scale it in using this U. So these will be the second row and second column and third column, and this is going to be the first column of the 3x3 determinant of 3x3 matrix. Okay, so I'm showing the rest of the part. So once you have this this whole thing written as in this form of wedge product of one forms, we replace this dP with the px dx, py dy, pz dz. So this is the first column happen to be the sum of three columns. So it distributes as if these are the product, and you have to keep the order correctly. So if you combine this dy and dy wedge dz, that's going to be the first column. Second column happen to be the same as the first column, scale multiple, so the determinant is going to be 0. If we look at the third column, dz is combined with the dz, so that third column is the same, the determinant is going to be 0. So determinant of this first column, this whole thing is the same as px dx wedge dy wedge dz, and that's all. That's all only thing that survives. If you look at the second part here, q is replaced with the dq. So let me write that in here. So I wrote it in here, and as you can see, so let's look at the second part. The dq expands exactly the same as p. So this is what the chain rule, if we have a parameterization, and we have this time dz dx, so dz dx. So whenever you have dz and dx here, the determinant is going to be 0. So the only thing that survives is dy. So it's going to be just qy dy dz dx. Here we have x and y, therefore only thing that survives is the z part. So let me circle those. So these are the only d part, that dx part, that's the only part that does not have a dy dz components, and therefore the determinant is not 0, so they survive. So they're all going to be dx wedge dy dz, dy wedge dz dx, and dg wedge dx dy. If you look at all those three things, these are scalar px and qy and rz, and these are column vectors, right? So they all have x and y in the same thing. So if you swap these columns, it's going to be exactly the same. But whenever you swap the two of the columns, the sign changes. So we keep dx wedge dy dz. If you look at it here, dy and dz dx. I'm going to write that down there. I wrote that in there. You can see dy dz dx. By switching these, you can rewrite this one as x, y, z order. So first I'm going to switch this to x and z. Then it's going to be dy dx dz. If I switch this one more time, it's going to be dx dy dz. So I swap this one 2 times. Every time you swap it, the sign will change to positive, negative, And if you did it 2 times, you'll go back to the original sign, which is positive here. So you can get that one lined up, dx wedge dy wedge dz, keeping the same, exactly the same sign. Let's look at it here. X and y is in good order. So if you swap z and x, that'll be dx dz dy. Swap this dz and dy, it'll be dx dy dz. Again, we swapped it 2 times, therefore we keep the sign exactly the way it is. So here I have written down, I lost that rewriting a little bit, but it's here. If you collect them, they're all lined up in this way. If you swap this properly, then we have px, qi, rz all in the same sign. Keeping the same sign, we're able to flip everything into dx, dy, dz. This is called divergence theorem, and we will use this cool theorem to compute the sum of the surface integral of a vector field in faster and better way. So for example, let's take a look at this example. F is the vector field, it's given up there, and S is the sphere, x squared plus y squared plus z squared equals 1. So relative to the inside region enclosed by the sphere, this one is oriented, let's say, outward. And we wanted to compute the surface integral. Ignore this this part for the moment. Surface integral of this vector field across this surface S. So by definition, or different notation, is that this surface integral is broken up into this dot product form. This has a z, y, x as a x and y, z component. It is multiplied to the xy component of the normal vector we choose, ru cross rv. So those dy wedge dz, and they came from the xy component of this one. Those are all determinant of 2 by 2 matrix, right? So this is what we are calculating. Again, by Curl's divergence theorem, what we do is that we realize that S is a boundary of the solid E, which is the solid ball, not the sphere, and S happens to be the boundary. Then we can bring that inside the triple integral. Let's see what happens. So here it is. What we're calculating is these are P and Q and R. By divergence theorem, if we look at this P, Q, R, X, Y, Z component of vector field, and we consider this scalar function, Px plus Qi plus Rz, which, if you do that, is simply just constant 1. This surface integral of vector field is equal to this triple integral of this scalar function, Px, Qi, Rz sum up to one quantity. It's dx wedge dy wedge dz. And that, if it's outward oriented, S is outward oriented relative to the solid E, and this dx wedge dy wedge dz is equal to dv. So I was trying to write it, this whole thing is going to be usual dv for the triple integral if this S is outward oriented relative to E. Okay, so this is simpler triple integral. So here's a simpler situation. We're computing the solid ball triple integral over the solid ball of this constant function 1. So it's actually the volume of this solid ball, but we're going to go through a typical change of variable because it's solid ball. The spherical change of variable, it's better, and I'm pointing out here S is outward oriented relative to E. In that case, we can switch to dv in there. So unfortunately, I didn't realize I didn't get the picture of the rest of the part, so I'm writing it in here in that space. But this is what we're calculating, the solid ball of the triple integral of the constant function 1 dv. Again, this is the volume, but I'm reviewing this parameterization. So here our goal is now calculating this triple integral, and because the solid ball is not kind of upright region or is a function of anything, so we use this change of variable, and that's the best. And spherical coordinate system as written here is the best one. So if you look at here, everything is varying freely. Rho is varying from 0 to 1, phi is covering everything 0 to pi, and theta is 0 to 2 pi. So therefore, we have to calculate under this change of variable the Jacobian, and we can rewrite this integral in terms of rho and phi and theta. The Jacobian of under this standard spherical coordinate change of variable is this Jacobian is rho squared sine phi. So when you rewrite this integral, everything just switches in terms of rho, phi, and theta, and dv is replaced by this Jacobian times d rho, d theta, and d phi. So which is written this way. So everything is multiplicative, can be multiplicatively separated. So if you look at rho square part, it's easily it's a 1/3 because the 1/3 rho cubed, and there's no theta part here. So this theta part 0 to 2 pi, just simply pick up the 2 pi, and then antiderivative of sine phi is negative cosine phi. So this 0 to pi picks up 2. So altogether is a 4 pi divided by 3. So that's an application of a divergence theorem. This is very, very cool theorem, and in the next part of the video we're going to look into that Stoke's theorem, and that's going to conclude the introduction to divergence and Stoke's theorem.